Hello everyone, welcome to the video lecture 15 on group theory. So this particular video is dedicated to my students, some of my students. I read their social media status that something like memories बनाने की उम्र में वो लोग assignment लिख रहे हैं. So I got motivated by that. I was also being lazy. I thought I'll teach tomorrow in the Google Meet class and then make a video. But then I thought my memories can wait for later. So I should be making video rather than making memories. So that inspired me to record video at this time of night. It's almost 1:30. So let us continue from where we left. So just yesterday I posted a video and now today another video. So let us recall what we have done. Before that, I would like to start with an exercise which I missed in the last class. So, the special video I am opening with an exercise which we have discussed, but not we have not. I did not state it. So, exercise is the first one. Prove that every disjoint cycles commute. Show that every disjoint cycles commute. Right, so we have seen this by examples. We take two disjoint cycles and we have seen that 1, 2, 4, that was 1, 3 cycle. Another 3 cycle was 3, 6, 5. And then they commute, that we have seen. So every disjoint cycles commute. The question is the converse true? Is the converse true? That means if two cycles commute, is it necessary that they are disjoint? So that is the question. This is to think. This is to prove. You can do both. You will find a counter example. So find a counter example. The converse is not true. I don't want to go back and record another new video. Okay, I made a blooper. It's okay. Second is this is very easy. Show that a cycle of length 1 is identity. Show that cycle of length 1 is identity. This is very easy. So as we have seen that 7 single cycle of 7 example. So let me give you a hint. So hint for the first one is we take 2 cycles. Now we are proving in general. See, not by an example. So suppose we have a cycle I1, I2, IR. And suppose we have another cycle J1, J2, JT. And they are disjoint. So none of this IK is same as JP, where K equals to 1 to R and P equals to 1 to T. None of this IK, K equals to 1 to R, none of this is equals to J1, J2, JT. So JP, where P equals to 1 to T. So they do not have any element common. So all these are distinct. Now what we have to show? They commute. That means let me call this theta equals to let us call this sigma 1 and let us call this sigma 2. Then theta equals to sigma 1, sigma 2, and call psi equals to sigma 2, sigma 1. Then what we have to show? We have to show that theta equals to psi. That means sigma 1, sigma 2 equals to sigma 2, sigma 1. So that is what we have to show. Theta of any element, any n, and not n, let us take some theta of k, equals to psi of k. So that is we have to show for all k in S. For all k in S. So there are 3 cases for k. What is the case? K equals to I1, I2, one of this, IR. Another case will be K equals to J1, one of this. In that case also they are equal. We have to show J1, J2, JR. Oh, sorry, JT. And the final case, k equals to uh, k does not belong to this set I1 I2. It is neither of this J1 J2 JT. K is not in this. So here instead of k equals to, I can consider this k belongs to this set. K belongs to this set, and k does not belong. Something is happening. I'm sorry. Yes. And so finally, k is not in any of the sets. So when you have to take three cases, k equals to I1 or any of this. K equals to I S, let us say IS, where IS, what is S? S is from 1 to R. Then the image of sigma 1, sigma 2 of IS under sigma 1, sigma 2. So IS will be sent to IS plus 1 in sigma 1. If S equals to R, then it is I1, and here it is identity. And on the other hand, first write this and then do it. So for this case is similar, all first and two, and then final. If k is not one of this, then k is fixed. Sigma 1 of k is k, sigma 2 of k is k. So k is identity. K is fixed by theta also, k is fixed by psi also. Just think about it. And second one is very easy. We have seen in the second one that cycle of length. So A is what? A is this 1, 2, 3, and somewhere there is A and N. Oops, again this happening. Yeah, and N. So A is what? So this is A is mapped to A, and all others are anyway identity. So 1 goes to 1, 2 goes to 2, and so on. Then N goes to N. So this is anyway identity. So that was this hint for the exercise. Just write this one clearly. That is the thing. So yes, these two exercises which I forgot. We discussed in examples, but I forgot in the last Google Meet also, and I forgot to in the video also. So that part I begin with, and then let us recall what we have discussed. So what we have discussed is this result. Every permutation can be written as product of its cycles. Every permutation can be written as product of its cycles. The cycles are disjoint, so every permutation can be written as product of its disjoint cycles. So that part we have seen. And then I had asked you an exercise to compute this 1 2 1 3 1 4. So this is a product of two cycles. What is two cycles? Cycle of length 2. So they are cycles of length 2. And then I ask you to compute this 2 3 2 4 2 1. And finally I had asked you to compute this one, that is 2 1 2 3 and 2 4. So I hope you would have computed this in S4. Let us say S4. So S4 is enough to consider in S4. 1 2 3 4. You can consider in S5 also, but then 5 will be mapped to 5 because 5 is not there in any of this. S6, if you consider, 5 is mapped to 5, 6 is mapped to 6. So let us compute this. So what about this? 1 goes to 2. So we can write this as permutation also. 1 goes to 2, first one, this 2 cycle. This 1 goes to 2, all others are identity. So 1 goes to 2, 2 goes to 1. So only 1 and 2 are interchanged. 3 goes to 3, 4 goes to 4. We can write that. Then we can write 1 3, then we can write 1 4, and then take the product. But we can do it directly. How we can do directly? We can multiply more than 2 cycles directly. So start with 1. Start with 1. What is image of 1? Image of 1 is 2. So now 1 goes to 2. Now look for 2 here. So there is no 2 here. There is no 2, so 2 goes to 2. And here also 2 goes to 2. So finally 1 goes to 2. Is it clear? Again, now what is the image of 2? So look for image of 2 in the first one. So in here 2 goes to 1. So now we are at 1. So now we see the image of 1 here. Here 1 goes to 3. And then here 3 goes to 3. So finally 2 goes to 3. Is it clear? Once again I am covering. I'm sorry, I removed this. Yeah. So now what about 3? So start with this one. Don't jump the cycle. Start with this one. Otherwise there will be mistake. Start with the first one. 3 is not there. So 3 goes to 3. 3 goes to 1 here in the second one. And now 1. So see the image of 1. So that is 4. So 3 goes to 4. And now finally 4. So 4 is not there in the first one. So 4 goes to 4. Second one also 4 is not appearing. So 4 goes to 4. And the third one 4 is appearing. So 4 goes to 1. So finally 4 goes to 1. So what this element has become is 1 goes to 2. 2 goes to 3. 3 goes to 4. And 4 goes to 1. So this is cycle 1, 2, 3, 4. Which can be written as, so this is a 4 cycle. 1, 2, 3, 4. Cycle of length 4. Which can be written as a product of 3 2 cycles. 3 2, not 32 cycles. 3 2 cycles. Right? So what about this one? Let us compute. So 2 goes to 3. But if you want to start from 2, you can start from 2, no problem. But I recommend start with 1. So that we don't make mistake. So 1 is not here. So in this cycle, 1 goes to 1. In this cycle also, 1 goes to 1 because 1 is not there. Finally, 1 goes to 2. So final image is 1 goes to 2. Now comes 2. Start with the first cycle. 2 goes to 3 here. So 2 goes to 3. Now come in the second cycle. 3 is not there. So 3 goes to 3. Third cycle, 3 is not there. So again 3 goes to 3. So finally this is 3. What about 3? So image of 3 is 2. Now check 2. Image of 2 is 4. Now check 4. 4 is not here. So 4 goes to 4. So that is finally 3 goes to 4. I can say 3 goes to 4. Now check image of 4. 4 is not here. So 4 goes to 4. So check again image of 4. 4 goes to 2. So now check image of 2. 2 goes to 1. So 4 goes to 1. So if I want to write this, being careful to remove this. Yeah. Okay, so what about this cycle? So this is 1 goes to 2. 2 goes to 3. 3 goes to 4. 4 goes to 1. So this is again cycle 1, 2, 3, 4. So this is a 4 cycle 1, 2, 3, 4. And now what about the other one? Let us compute this. 2, 1, 2, 3, 2, 4. So start with 1 and from the left side first cycle. So 1 goes to 2 here. So check the image of 2. 2 goes to 3 and 3 goes to 3 here. So finally 1 goes to 3. As you can see, there is difference. Both cycles 1 goes to 2, 1 goes to 2, here 1 goes to 3. So there is going to be some difference. And let us observe what difference it is going to give us. So now what is the image of 2? So 2 goes to 1. 1 goes to 1 here. Again 1 goes to 1. So finally 2 goes to 1. Now what about 3? So image of 3. So 3 goes to 3 here. 3 goes to 2 here. And 2 goes to 4 here. So 3 goes to 4. Right? If you find it fast, then stop the video. Repeat it again. Rewind it. And listen again. What about 4? So 4 goes to 4 here. There is no change. Look for the image 4 here. So and finally here also 4. We see 4 goes to 2. So finally this. And you can check we have got all distinct entries. 3, 1, 2, 4. 3, 1, 4, 2. So what is this cycle going to be? 1. 1 goes to 3. 3 goes to 4. 4 goes to 2. And again 2 goes to 1. So this is 1, 3, 4, 2. So it is not 1, 2, 3, 4. So there is some difference here as a product of 3 2 cycles. Cycles of length 2. There are 3 cycles. But as you can see, this is the order. 1, 2. 1, 3, 1, 4. So that is giving us 1, 2, 3, 4. Right? So, oops. Okay. So as you can see, 1, 2, then 1, 3, 1, 4. So it is giving 1, 2, 3, 4. Then here, 2 3, 2 4, 2 1. So what should we expect? We should expect, if we do like this, 1 2 1 3 1 4. So we are getting 1 2 3 4. So here also we have 2 3 2 4 2 1. So we should have 2 3 4 1, and that is the same thing. See, 2 3 4 and 1. It is the same cycle, 2 3 4 1. What about this? This is, you can check, 2 1 2 3 2 4. So this is going to be 2 1 3 4. So 2 is coming first, and then we are repeating, I mean we are writing this element. So 2 is the first one to appear, then 1 3 and 4. So 2 1 3 4, which is same. 2 goes to 1, 1 goes to 3, 3 goes to 4. So these two cycles are same, but the third one is not same. The thing is that 1 2 3 4, we have reversed the order. So 1 2 1 3 1 4, so that the order is same. Then if we start from 2, we should not take 2 1, we should take the same order. After 2 comes 3, so 2 3 2 4 and then 2 1. So if we write 2 1 first, 2 1, then it is not going to be the same. Yeah, so I hope this example is clear, and if you have tried, then this would be clear to you. But now coming to the point that every cycle can be written as product of two cycles like this. In general, any cycle I can write as product of two cycles. For example, if I am given something like this, okay, just a minute, I need to add more pages. Yeah, I added, let me add a few more pages. Yes. Okay. So now, yes, as another example, let us consider this cycle 3. Just consider the same cycle 3 6 5, which we had considered last time. So we can write this as 3 6 3 5. Can we write like this? Yes. Let us check. What is this 3 6 3 5? So 3 6 3 5. So remember, you can write this as a permutation also. 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. 3 goes to 6 and 6 goes to 3. 3 goes to 5, 5 goes to 3, and then multiply this. That is a long way, shortcut technique, as we have done here. So this will be what? Start from 1. See, 1 is not here, but start from 1. So 1 goes to 1. So if I want to write this as 1, 2, 3, 4, 5, 6, 7, then start from 1. 1 is not appearing in the first cycle, so 1 goes to 1. In the second cycle also 1 is not there, so 1 goes to 1. What about 2? In the first cycle 2 is not appearing, so 2 is identity. Second cycle 2 is identity, 2 goes to 2. Yes, what about 3? 3 goes to 6, and then here see the image of 6. 6 is identity because 6 is not there. So 3 goes to 6 and 6 goes to 6, so finally 3 goes to 6. Now 4. 4 is not there, so 4 goes to 4, 4 goes to 4. So that means image of 4 is 4. Now see 5 here. So 5 goes to 5, no problem, no change. But then here 5 goes to 3. So ultimately 5 is mapped to 3. What about 6? 6 is mapped to 3, and here both changes there. So 6 is mapped to 3, and here see the image of 3, that is 5. So 6 is mapped to 5. Yes, and what about 7? 7 is identity, so that is fine. So what is this cycle going to be? This will be 1 is identity, 2 is identity. Start from 3. So this is 3. 3 goes to 6. 6 goes to 5, as you can see here, and 5 goes to 3 again. So this cycle is over. And rest other side identity we want to write, we can write like this: 1 2 4 5 7. If you want to omit this, we can as well omit this, no problem. But as you can see, these are the changes: 3 6, 6 goes to 5, and 5 goes to 3. Right, so this is the cycle. And here, as you can see, so this cycle we can write as 3 6 3 5. What is 3 6 3 5? So write first 3, and then so write first 3. So 3 comes, and then 6, and then 5. And this, and this. So this is the way to write this cycle. There is another way to write the same cycle. How do we write? If I suppose I want to start from 6, what should I consider? Not 6 3. It should not change the order. So if I want to write this as product of 2 cycles, so it should be 6 5 and then 6 3. If I want to write as start from 5, then 5, it should not be 5 6. It should be in the order. So 5 3 and it should be 5 6. Yes. So you can check that these are the ways one can write. Not only that, I can write this also this as so this one can be written as instead of 3 6, I write 6 3 and 3 5. This is one and the same thing. Why? Because this is same. So note that. 3 6 is same as 6 3. Why? What is this? Permutation 3 6. It fixes all others identity. So it fixes all other elements. That means it is identity on all, acting on all other elements. 3 goes to 6 and 6 goes to 3. What about 6 3? 6 3 also says same thing. 6 goes to 3 and 3 goes to 6. So 6 and 3 are interchanged. So they are same. So in general a 2 cycle can be written as, in general, I comma j is equals to j comma I for every 2 cycle. For every 2 cycle. Let me write like this, 2 cycle. So that is cycle of length 2. Ij is same as ji. So it does not matter which order you are writing. We know we can write one cycle in many order, many expressions. So 3 6 5 can be also written as 6 5 3. It can also be written as 5 3 6 using the same order. Right? So 2 cycle, if we change the order, it is going to be the same thing. It is not going to be different. Yeah, so that means every so this cycle also can be written as product of 2 cycles. So that means can we write every cycle as product of 2 cycles? So that is the general exercise. Again, yes, exercise I'm going to leave you. I'm giving you the hint. So the theorem, let me state the theorem. Every cycle, okay, before theorem, let me define this a new word for 2 cycles. So the definition, a 2 cycle, that is a cycle of length 2, it has a special word, so is called a transposition. Yes, what is a true 2 cycle? It is called a transposition. Especially this is a word for transposition. It changes the position I to j, j to I. So that is special word for 2 cycle. No other cycles have got special word. Cycle of length 2, they are also called transpositions. All cycles of length 2. So then now the result is uh, every cycle, any cycle can be written as a product of 2 cycles. So every cycle can be written as a product of 2 cycles, a product of transpositions. Let me use this word, transpositions, that is 2 cycles. So every cycle can be written as product of 2 cycles. This is the thing which I ask you to prove, and I leave as exercise. But I'll give you a hint how to prove it. So you can see from this example, 1 2 3 4 can be written as 1 2 1 3 1 4. Yes, similarly 3 6 5 can be written as 3 6 3 5. Also 6 5 6 3. That is also, so it is not unique. The expression is not unique. That is clear. But now we want to prove that every cycle can be written as a product of transpositions. So that means we have to prove like this. So hint something. Let me give you a hint. So I consider a cycle theta. Theta equals to, let us say, I1, I2, IR. So this is a R cycle, or a cycle of length R, also cycle of order R. And this we want to write as product of transpositions. So if we write psi equals to, how do we write? The same technique apply here. So here 1, 2, 3, 4, how did we write? 1, 2, 1, 3, 1, 4. So just take this same thing. So I1, I2, sorry, I1, I2, IR. If I want to write as product of two cycles, that is product of transpositions, how do I do it? I do it like this. So I1, I2, that is the first two cycle. Another two cycle I1, I3, I1, I4, product. So it is not comma, it is product I1, IR. Right? So now what you have to show to prove? Psi equals to theta. On one side, what is psi? Psi is product of all two cycles. And what is theta? Theta is this R cycle. And we have to show that they are same. So how do we show that they are same? So that means we have to consider again three cases. K equals to I1 to IR minus 1. What happens if I take K equals to I1 to IR minus 1? I am giving you the proof almost, not the hint. So theta of I, or theta of, if I take IK equals to 1 of this, then what is theta of IK? It is going to be the next one, IK plus 1. Oh, sorry, IK plus 1. It is going to be the next one, IK plus 1. Right? If I1, what is the image of I1 under theta? So I1 goes to I2, I2 goes to I3, up to IR minus 1. IR minus 1 goes to IR. Then another case is this, IK equals to IR. So K equals to R. So what is theta of IR? In this case, it is not IK plus 1. There is no IR plus 1. So in this case, it is IR goes to I1. IR goes to I1. And uh, finally take A. A is not any of this. I1 to IR. A is in the set S, but it is not in any of them. The theta of A is A. If it is not appearing in the, it is identity. Now what you have to prove, just you have to prove that this is same of psi of IK. In this case is IK plus 1. So this much you have to prove. So if I take IK, suppose K equals 2 or K equals to 3, then I3 is not changed here because I3 is not appearing. Here it is appearing. I3 goes to I1. In the next one will be I1, I4. So I3 goes to I1, I1 goes to I4. So finally I3 goes to I4 because I4 is next. It is not coming at all. So that you have to argue, write a general proof of this. This is an exercise. Right? So in this one, theta I psi IR equals to I1, and then here if A is none of this IP, then I1, I2, IR, it is none of this, then it is psi of A is also A. So the product is same as theta, so R cycle. So this is the general result which I ask you. And as a corollary, finally, what you have, if I combine these two results, what is the result that we have seen in the last video lecture? The result was not this, yes, here, recalling the thing. Every permutation can be written as product of its disjoint cycles. Now, what we prove here in this theorem, every cycle can be written as product of two cycles, so product of transpositions. Every permutation can be written as product of cycles. Every cycle can be written as product of two cycles. So finally, as a corollary, we can write every permutation can be written as product of two cycles. So every permutation, so let me write here, every permutation can be written as a product of transpositions. Of course, this is not unique, right? As we have seen, the transpositions can be written in different ways. product of transposition, that is as a product of two cycles or cycles of length 2. So the proof combining the above two results. The proof follows. Right, so every permutation can be written as product of cycles, disjoint cycles, and here in this theorem we prove that every cycle can further be written as product of two cycles, that is transpositions. So finally every permutation can be written as product of transpositions. For example, consider our theta. So for example, we had considered this example given by Nirav at that time. So 1, 2 permutation in S7, 3, 4, 5, 6, 7. And what he gave is 1 goes to 2, 2 goes to 4, 4 goes to 1, 3 goes to 6, 6 goes to 5, 5 goes to 3, and then 7 to 7. So this we express this theta as product of cycles, disjoint cycles 1, 2, and 4. Another, there was a 3 cycle 3, 6, 5, and another one is 7. Right, so how do we write this as further? This I can write as 1, 2, 1, 4. What I have written? I have written this 3 cycle as product of these 2 cycles 1, 2, 1, 4. Right, so this is 1, 2, 1, 4. And what about this? So this can be written as, how can we write this? This can be written as 3, 6, as we have seen above, 3, 5 in the same order. And what about 7? 7 I can omit because it is identity. So this is, or I can write this in another way also. 1 instead of 1, 2, I can write this as 2, 1. So there is another way which we have already discussed, that ij equals to ji. So that is fine. 2 disjoint cycles commute also. So I can write this as this is 1, 4, and 3, 6. I can interchange this, no problem. They are disjoint. Right, so they are disjoint, so I can write this as well. 1, 2, 3, 6, you can check. 1, 4, and 3, 5. They are disjoint, so they commute. 1, 4 is consisting of 1 and 4. 3, 6, so no element in common. So 3, 6, and 1, 4 can be interchanged. So that is why I wrote this exercise, because we are going to use it frequently. So that every disjoint cycles, every 2 disjoint cycles, or any 2 disjoint cycles commute, right? And converse is not true. Okay, so, and again these 2 also can commute, so there is no problem. Similarly, this 1, 2 also can be jumped. So this 1, 2, 1, 4 can be written in the right side, and 3, 6, 3, 5 can come here also. So there is not a unique way, but we can write. And what about 7, as we had seen? What about 7? What happens to the 7? How do we write 7 as product of 2 cycles? But 7 is identity. 7 is identity, so we can omit, no problem. So here we have 2 cycles in this expression. What we have? 4 2 cycles. Right? So that means 4 cycles of length 2. 4 cycles of length 2. And 7 is omitted. But what happens to 7? That is a question. Because here every cycle can be written as product of 2 cycles. So single cycle, if I take A, or let us say 7, what happens to that? How can we write this as IJKL? So this is the biggest question here. How do we write this? So think about this, right? About this theorem. How do we apply this theorem to this? Can we write like this? It is a question. So think about it. So 7 we can write maybe. So then we have to include this. So then the number is not 4. It can be more. Right? So it can be more. So it is not 4. So is it going to be 4 always? Or is it going to be increasing? Yes. Okay. So this is not unique, but finally every permutation can be written as disjoint product of disjoint cycles. Every cycle can be written as a product of two cycles, that is transposition. So ultimately every permutation can be written as product of transpositions. And here this example we have written this permutation as how many transpositions? Product of 4 transpositions. So 4 transpositions are there. So in this case 4 transpositions, which is an even number, which is not always the case. In some case, it is an odd number of transpositions, odd number of 2 cycles. So here 4, 4 is an even number. So the definition is, now we define what do we mean by even permutation and odd permutation. Definition: if a permutation can be written as if a permutation can be written as a product of even number of transpositions, even number of transpositions, then it is called an even permutation. And similarly, if a permutation can be written as odd number of transpositions, then it is called an odd permutation. So let me write here. If a permutation can be written as a product of odd number of transpositions, then it is called an odd permutation. So this is odd permutation, even permutation. Sorry. Yeah. Odd and even permutation. Right. So a permutation can be written as a even number of transpositions, then it is called even permutation. If it can be written as a product of odd number of transpositions, then it is called an odd permutation. So above example we have considered, this is an even permutation, right? So this is an even. So it's an even permutation. Why? Because there are even number of 2 cycles, even number of transpositions, 1, 2, 3 and 4, 4. Either 4, 2, 6. So then it is an even permutation. Now the question is, what happens if so there are, this representation is not unique as we have seen. So this is one representation, this is another representation. So there are 2 representations and many more maybe. Also we can write this in many different forms. So 2 representations, and suppose, and even more, if we write this 7 as, if 7 can be written, I don't know, if the theorem says every permutation can be written as a or every theorem says every cycle can be written as product of transposition. So a single cycle is also a cycle. Identity element also should be written as product of 2 cycles. How can we write one cycle as product of 2 cycles? So one cycle can be written as a product of 2 cycles or 3 cycles or 4 cycles. Is it possible? So if that is possible, then this number is not 4, even more. If because the permutations of this transpositions of 7 are also going to come in picture, this number may increase. What if this number becomes odd number at the end? So should we call theta as an odd permutation or even permutation? That is the question. So we have defined a permutation is called even permutation if it can be written as even number of transpositions. It is odd permutation if it can be written as odd number of transpositions. So here theta, this example we have considered, it can be written as 4 number of transposition in this expression. This is another expression, but just a small change. 1, 2 I have written as so this, they commute 1, 2 I can write as 2, 1 also. So that is not a problem. But the number is at least same, even. But what happens if the number changes in other representation? So should we call it even permutation or should we call it odd permutation? So the answer is, this is never going to happen. If you write a permutation as product of transposition in even number of transposition in one representation, you take any other representation, कोई दूसरा representation ले लो, उसमें even number ही होगा. यहाँ पे 4 है. If you take any other representation, the number is going to be even. I am not saying the number is going to be 4. The number is going to be even. So either write it as product of 4 transposition, or you can write as product of 6 transposition, or whatever the number, but it will be an even number. So this is what we are going to prove, that if it is even number in one representation, it is always going to be even number in other representation also. So for that we introduce a polynomial in n variables. So this is the polynomial. So notation, Pn we now prove that even permutation will remain even permutation in any representation. कैसे भी लिखो उसको, even number of transpositions ही आएंगे. Number may not be same, but it will be always even number of transposition. An odd permutation, that it can be written as odd number of transpositions, odd number of 2 cycles in one representation. Then in any representation, the number of cycles, 2 cycles, will be always odd. So that means the definition makes sense. So it is not, it's a well-defined thing. So notation for we introduce this Pn. So we introduce Pn, x1 polynomial in n variables, x1, x2 up to xn, and this is defined as, so Pn equals to x1 minus x2 in this order. Then we have x1 minus x3, and then x1 minus xn finally, and then x2 minus x3. We don't go back, we start from the next, x2 minus x4 up to x2 minus xn. So what comes next? x3 minus x4 and so on. So this goes on कब तक? xn minus 2 minus xn minus 1, next one. Then we have xn minus 1 minus xn, and xn minus 2 xn, and then xn minus 1 minus xn. So this is the polynomial in n variables. So for example, let us take a particular case. For example, take P4. What is P4? P4 is a polynomial in 4 variables, x1, x2, x3, x4. Let us write this. So this is going to be x1 minus x2, x1 minus x3, x1 minus x4, and then x2 minus x3, x2 minus x4, and then one more thing. So x3 minus x4. Is it clear? So x1, x2, x3, x4. So start with x1. So we have 3 terms: x1 minus x2, x1 minus x3, x1 minus x4. Then x2, go further, don't go back. So no x1 and no x2 coming. So x2 minus x3, as you can see here, x2 minus x4. So x4 is the last one. Then comes x3, x3 minus x4. That's it. So this, if you want to write in terms of a general product, so this can be written as, we can write this as, we can write this as a product I equals to 1 to n, but I less than j. I equals to 1 to n, I less than j, xi minus xj. Xi minus xj. Right, so this is the product which we can write. So this is Pn. General Pn can be written like this. So start with I equals to 1, then j must be greater than I, so j starts from 2, and so on, and I equals to 2, then all these elements, product of xi minus xj. So take this. So this is the polynomial which we introduce, and now we define the effect of permutation on this polynomial. So what is the effect of a permutation on the polynomial. So definition. So let us take some theta in Sn. Yes, then what is defined? We'll take an example later on. So define theta of Pn. What is theta of Pn? So this is going to be theta of Pn and x1, x2. So Pn is in n variables, so x1, x2, xn. And this is going to be theta of Pn will be Pn, again n variables, but not x1. It will be x of theta 1, x of theta 2, and so on up to x of theta n. So again, it's a polynomial in n variables only, and those n variables are x1, x2, xn only, but the order has interchanged. The order has interchanged. So what is the order it has become? So so that is, we can write uh, this theta. What was Pn? Pn was written in the terms of product like this. So theta of product I equals to 1 to n, I less than j, and xi minus xj. This can now be written as product I equals to 1 to n, I less than j. Some problem here. And x theta of I minus x theta of j. X theta I minus x theta j. Right, so this is the effect xi instead of xi, whatever, wherever the I element is there, so x1. So in the polynomial, in the definition of polynomial, x1 is replaced by theta of x of theta 1. So if theta sends 1 to 3, x1 is replaced by x3. If theta sends 2 to 5, x2 is replaced by x5. So then it's just permutation of this. So here also the order will change. So this all x1 goes to x5, so some other term will come. So let us see what is the effect. So let us consider one example to understand this better. Let me, yeah, so let me take in this itself. So polynomial with 4 variables, and let us take theta equals to, so as an example, let us take 1, 2, 3, 4. Let us say 1 goes to 4, 4 goes to 3, 3 goes to 1, and 2 is 2. Right, so theta is with cycle, 1 goes to 4, 4 goes to 3, 3 goes to 1, and 2 is 2. So this is, we can write 1, 4, 3. 1, 4, 3. So that means what is theta of P4? Theta of P4, x1, x2, x3, and x4. This is going to be P4, x1. Instead of x1, we have x4, because x theta of 1. What is theta of 1? Theta of 1 is 4, theta of 4 is 3, and this is this. So x, instead of x1, we have x4. What about x2? So 2 goes to 2, so x2 remains as it is. Then 3 goes to, so 3 goes to 4, 3 goes to 1 here. So that x3 will be replaced by x1. And finally 4 goes to 3 here, so x4 is replaced by x3. So again we have in x1, x2, x3, x4 only, but the order has interchanged. The theta has replaced this. So what is the polynomial is going to be like? If I want to write this in terms of the definition of this, like this, what it is going to be, let us write this down. So this is going to be it will easy to write from this. So let me write from this. So x1 minus x2. So x1 minus x2 is going to be replaced by x1. 1 goes to 4. So x4 minus x2 is same. So x4 minus x2. So that is same. Then x1 minus x3. x1 minus x3. X1 is going to x4. So this is going to be x4. And what is x3? x3 has become x1. So this is x4 minus x1 because 3 goes to 1. Then it is x1 minus x4. But x1 is what? x1 is x4 because 1 goes to 4 here. So x1 is x4. And what about x4? x1 minus x4. x4, 4 goes to 3. So it is x4 minus x3. Then x2 minus x3. x2 is not changing because image of 2 is 2. So 2 is identity. So x2 is same and minus x3. x3 has become x1. And then x2 minus x4. So x4, x2 minus, so x2 is same as x2. x4, 4 goes to 3. So this is x2 minus x3. And finally this guy, x3 minus x4. So 3 goes to 1, so that becomes x1. And x4, 4 goes to 3. So this is x1 minus x3. Let me copy this and let us compare what has happened. So this we copy. And let me copy and then continue. Okay, so this is theta p4 and p4. I have written both of them, and now we can compare. So in theta, this is x1 minus x2, x1 minus x3, x1 minus x4 in p4. Then x2 minus x3, x2 minus x4, and x3 minus x4 finally. So this is theta, sorry, this is p4. Now theta p4. So x1 minus x2 is here. So is x1 minus x2 available elsewhere? Here and here. So this is x2 minus x1. So there is going to be a minus sign. So I can write this is minus 1. Okay, what about x1 minus x3? x1 minus x3 is here. So this is no problem. And then we have x1 minus x4. x1 minus x4, but this is x4 minus x1. So there is a minus sign. And then x2 minus x3 is here. What about x2 minus x3? This is same. So no problem. So this is x2 minus x3. And then x2 minus x4. Is it? So x4 minus x2. So this is again minus 1. And then finally x3 minus x4. Here we have x4 minus x3. So this is minus 1. So how many times minus appearing? So 4 times minus is appearing. So this is same. If we just multiply by minus 1, this is going to be same. Just order is changed. So in this case, we observed theta p and theta p4 equal to p4 itself. But sometimes this number of signs, because this theta is an even permutation, so this is we can write as 1 4. So this can be written as 1 4 and 1 3 as product. So this is product of two cycles, product of two transpositions. This is an even permutation, so the sign change is not there, but otherwise the result is this, which we are going to accept without proof. So this is the lemma, and the proof is given in my old lecture notes, last year's lecture notes. It was given by Karya sir, but it is not given in book, and we are not concerned with this also. It is not in asking the Herstein to verify this also, so we are not going to include this in this time revision. But if you are interested, you can see this proof. So theta belongs to Sn. Then theta of Pn. Theta of Pn is nothing but it is plus or minus P, and it will just change the sign. It will not do anything else. It will just change the sign of this. So we accept it without proof. So what is interesting to us is not theta as in general permutation. What is interesting to us is this lemma. What about transposition? So if phi is a transposition, in Sn, then phi of Pn is minus Pn. Phi of Pn is minus Pn. So consider this example P4, right? Take transposition phi. So phi of phi equals to, you can take 1 goes to 3. This is transposition, 1 goes to 3, 3 goes to 1, and then apply in P4. So check what is phi of P4. Phi of P4, it is going to be minus P4. So in general, if phi is phi equals to ij, then phi of P4 or phi of Pn, here it is going to be minus Pn. So this is uh, the proof I give you as exercise. This will be an assignment exercise. You can make memories meanwhile. Then when the assignment is assigned to you, this question, you can write this assignment and submit. So this is, I leave as an assignment exercise, class assignment, right? So this is general, and then take the case, what is phi of p, and the proof is given in my old lecture notes. In the new lecture notes, I'm not going to include this proof, but consider phi as ij, and then see what happens. Xi will be in Pn, xi will become xj, and xj will become xi, and then see what is the change here in this general form. X1 minus x2, all this will be same, where xi will be there, xj will come. So you will have three cases. I can give you a hint. If you have I less than j, I less than, so we'll have I less than k less than j. This is first case. The second case will be I less than j less than k, and the last case will be k less than I less than j. Something like this you have to consider. Then there are three terms. What happens to this? Xi minus xk. What happens to, in all these three cases, xi minus xj? Xi minus xk, it is going to be same, and here there is xk minus xi in Pn, because k is less than I, so it is going to be this, right? So what becomes when we apply phi? So what happens if I apply phi on this? So when phi is applied, what happens? Phi is the transposition, what it gives, right? So just check this. So these three cases. So that is the hint for the assignment exercise. Right, so that is important. So the transposition, uh, two cycles will just change the sign to minus. Phi of Pn is minus. So this is important to us. In general, permutation is not important, so we skip the proof. But in Herstein, it is asked to verify this. So in general, you can verify. You can take particular example also, as I said. You can take 1, 3 and check this one, whether this is happening or not. Right. So, and now we prove that whatever we claimed as a corollary of this lemma, that if a permutation can be written as even number of transposition in one representation, then it can be written as in every representation it is even number of transpositions. So if a permutation theta, if a permutation theta can be written as a product of even number of transposition, similarly odd number of transposition, right? So that also works. So even number of transpositions, even number of transpositions, that is two cycles. So if it is an even permutation, transpositions, transpositions. At this time it happens 2:30 almost. if a permutation theta is an even permutation, so it is written as a product of even number of transposition in one representation, then in every representation, in all other representation, it can be written as even number of transpositions. So it can be written as even number of transpositions. That means it is always be an even cycle. The number of transpositions will be even in any representations. So the proof is very simple. Proof let theta belongs to Sn is can be written as even number of transpositions. So even number of transpositions. Say, suppose I write theta as theta equals to, now these are transpositions, so phi 1, phi 2, this is phi 2k, even number of transpositions. Then what happens? What about theta of Pn? Theta of Pn is going to be, we are applying theta in on this, so that will be theta of Pn, that means theta is applied to Pn, so this I can write as theta Pn, this is same as theta of Pn, which is phi 1, phi 2, phi 2k of Pn. So this means first phi 2k of Pn is applied. So phi 2k of Pn is applied. So that phi 2k is nothing but it's a transposition. All these are transpositions. So there are two cycles. So two cycles, what is the effect of two cycles? Is just changing the sign to -1. So phi 2k is applied, Pn becomes minus Pn. Then phi 2k minus 1, the previous one will be applied. Minus Pn will become Pn, plus minus 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 and so on, that will become plus, because these are even number. So these are even. What is going to give us? It is going to give us Pn, right? It is minus 1 power 2k Pn, and that is going to Pn. So theta will have no change on this, right? And now suppose in another representation, suppose theta equals to, these are transpositions, psi 1, psi 2, let us say psi r, where psi i's are transpositions, are transpositions. Then what we have to prove? We have to prove that R is even. So this is one representation where we have even number of transpositions. Then in any other representation, suppose this is another representation, psi 1, psi 2, psi r, then we have to show that R is even number. Again, we know what is theta Pn. Theta Pn is Pn. So then Pn can be written as theta Pn, and theta, that will be nothing but psi 1, psi 2, psi r, and applied on Pn. So first psi r will be applied on Pn. Psi r is a transposition, so it will be changing Pn to minus Pn. Then psi r minus 1 will be applied. Again it will change to minus Pn, so minus minus plus, so it will become Pn, then so on. So this becomes minus 1 power r Pn. So when you have on one side Pn and on the side minus 1 power r, so you can say that this implies r equals to, so r is even. So this proves our corollary that this representation is also even. It need not be same, as I said, the number is even. If theta can be represented as 4 transpositions, it can be either represented as 6 transpositions or 2 transpositions or 8 transpositions, but its number is always going to be even. It need not be same. Okay, so this being done, now, so we consider this even, that is why we consider these transpositions. The theory has come. So these even permutations are special. I am running page, so I ran out of page, so I added one page. Where was I? Yeah. So the even number of uh, even permutations are special. So now let us take that. So notation, let an denote the subset of or the set of all even permutations. Let an denote the set of all even permutations in Sn. So that is an equals to all those theta in Sn, so that theta is even. What do we mean by theta is even? Theta is even means theta can be written as product of even number of transpositions. For example, if you want to consider uh, for example, if I consider theta as 1, 2, 3, this is 1, 2 and multiplied by 1, 3. So this belongs to A3. This is in S3. S3 we know E psi phi, so this is actually psi. Right? So psi is 1, 2, 3. 1 goes to 2, 2 goes to 3, and 3 goes to 1. So this is psi. And then that can be written as product of E. So that is in A3. But if I write theta as phi, so theta equals to phi, and what was phi? Phi was 1, 2, 3. So 1 goes to 2, 2 goes to 1, and 3 to 3. So this is nothing but 1, 2. Only 1 and 2 are interchanged. So this is not in A3. So this is odd because the number of transposition is 1. This is odd number. Here the number of transpositions are even. There are two number of transpositions. So 2 cycles are even, here 2 cycles. So An is the set of all 2 cycles. Right? Set of all, not 2 cycles, sorry. It's set of all even permutations. Then the exercise I ask you to do is, which I will prove here, but in a different manner. I ask you to prove it independently. So I ask you to prove this one independently. Show that An is a subgroup. An is a subgroup of Sn. So An is a subgroup. So if I multiply two even permutation, it is going to be an even permutation. So suppose one permutation can be written as product of 4 cycles, which is even number. Another permutation can be written as product of 6 2 cycles transposition. Then the product will be written as product of 10 transpositions. So then, or you can cancel out also, but the product will be even. Even into even, that is going to even plus even, the transposition, that is going to be an even number. So product of 2 even permutation is going to be even. And similarly, what about inverse? So if you show that it is closed under operation, the product composition, and it has every element has an inverse, then it is a group. On the other hand, the set of odd permutation is not going to be a group, because if you take odd permutation, another odd permutation, suppose this is product of 3 cycles, this is product of 3 cycles, so multiply them, you will have 6 transpositions, sorry, not cycles, transpositions, 6, 3 plus 3, which is going to be even. So odd is not going to work. Even identity will not be, identity also will not be there. So that is not the case, but this is interesting. Set of all even permutations, this is a subgroup of Sn. Is it a normal subgroup? Again, after making memories, you can write this assignment. Is it a normal subgroup? That is a question, right? And now I prove this. I ask you to do this independently, and now I prove the same thing uh, in next. So the lemma. So multiplication of 2 minus 1 into minus 1 gives 1. So two odd things, we add them, it gives us even number. Two even things, it gives even. One odd and one even, even. So minus 1 into 1. So that is the idea behind this. So let W be the group. So W be the group minus 1 1 under multiplication. So W is this group, and define psi from Sn to W. So we have, how do we define? By, so we have psi of theta. So if I consider any theta here, with psi of theta, it is either assuming these two values, 1 and minus 1. So where should we give 1? This kind of examples we have seen. Where should we give 1 if theta is even? Theta is even. And minus 1 if theta is odd. So Sn, any permutation, either it is odd or even. So if it is even, then 1. So if you multiply two even permutation, it is going to be even again. So 1 into 1 is 1. If you multiply two odd permutation, it will be even. So minus 1 into minus 1, so that is 1. Odd and even, so that is going to be odd. So minus 1 into 1, so that is minus 1. So that means this theta, we have to show that this is a homomorphism. So then, sorry, not theta, this map psi. Psi is a homomorphism. And kernel of psi is this group AN. Kernel of psi is all those elements which are mapped to identity. What is the identity of this group? It is 1, multiplication, so it is 1. So 1 ઉપર કયા map થાય છે? All those even permutations are mapped to 1. So even set of even permutation, that is AN. So kernel of this is very trivial. Kernel of psi is AN. Just verify that this is homomorphism, and your guess is right. What is going to happen? Yes, that's true. This is also an exercise just to verify this psi is a homomorphism. Of course, kernel of psi is equals to A, and this is just from the definition. It is going to be A. So this is again, it is coming in assignment. So this was all pre-planned, not because of your any statuses or memories. This was going to be the same. In my notes also I have written that this is an exercise. So as a corollary, what happens is we can conclude homomorphic image of group is also. So psi of Sn, that is, I mean, kernel is always a normal subgroup. So what as a corollary we have? First thing, we have An is a normal subgroup of Sn, and second one, order of An equals to order of Sn upon 2, which is nothing but it is n factorial by 2. So the proof, what is going to be? No, this is not exercise. Your guess is wrong. I'm going to do this. It's just homomorphism. If you prove, then the first one, An is normal subgroup, but if you show that kernel of psi is An, kernel of any homomorphism is a normal subgroup. So kernel of any homomorphism, kernel of any homomorphism is a normal subgroup. It is a normal subgroup of the domain group. Whatever the group we consider in the domain, it is going to be a normal subgroup of the domain group. And so by above lemma, if psi is a homomorphism, kernel of psi equals to An is a normal subgroup of Sn. So that is the first thing. And what about second? So by first isomorphism theorem, if this is a homomorphism, then what happens? First isomorphism theorem, psi quotient kernel of psi is isomorphic to the image of psi. So by first isomorphism theorem and above lemma, if we combine these two together, then G quotient kernel of psi. So G is Sn. Sn quotient kernel of psi is isomorphic to the image of psi. Image of psi is onto. 1 also is there, minus 1 also is there. Odd permutation, even put. So this is image is W, which is so if they are isomorphic, then order of Sn quotient kernel of psi, this implies order of Sn quotient kernel of psi is equals to order of W, but this implies order of Sn upon order of kernel size An. Kernel size, so An is order of W is 2, 1 minus 1. So this is order of An will be nothing but order of Sn by 2. Sn by 2, what is order of Sn? If S has n elements, Sn has n factorial. So this is n factorial by 2. So exactly there are half number of odd permutations. There are half number of even permutations. Right, so this being done, and let me define. So what is this An? The An is called alternating group. So the subgroup An of Sn of order n factorial by 2 is called the alternating this is called alternating group. And what is index of An? So from this the second, so from 2, what we observe? We observe that index of An in Sn, index is nothing but order of Sn upon order of An, which is n factorial upon n factorial by 2, which is nothing but 2. So index of An is 2, and An is a normal subgroup. So by above corollary, in other words, we have this result. I can write this as a lemma, which we already proved. There's nothing to prove here. The same thing I am restating here. So Sn has a normal subgroup, which we know what is a normal subgroup. An. Sn has a normal subgroup of index 2. And what is that? The alternating group. The alternating group An, consisting of all even permutations. All the even. Okay, so this completes this section, and we are done. Thank you. This video also has gone past 1 hour, I'm sure. And just see this. If you have any doubt, just repeat it, and then we can discuss in maybe tutorial sessions. Thank you.